The universe tends to lead to balance. We find balance in nature and many more. The science term we use to describe this is equilibrium, which we've all heard before. When the balance of a natural system is disrupted, we can say it's out of equilibrium. However, that's not always a bad thing. Nature always finds a way to restore balance. In a chemical reaction, we tend to think about it having a beginning and the end, but that's not always the case. You don't usually end up with a pure product. Many chemical reactions tend to seek balance, just like us. They have to work through the stress in order to find their balance. Like I said before, in reality, many reactions are never finished. When the reactants react with the formed product, it's called a forward reaction. There is also an opposite reaction that occurs with the product changing back into the reactants. This is called a reverse reaction. React Reactions are reversible when they go forward and backwards without any extra energy being used. Remember that billions of reactions are happening during the process. Some of them may go one way and the others will go the opposite way. When the forward and backward reaction occurs at the same rate, it's called a chemical equilibrium. We can think of it as this. If the person who is digging the hole is bigger than the person who is filling it, we can call this a forward reaction. If the person who is filling the hole bigger than the person who is digging it, this would be a reverse reaction. In addition, if both people are equally distributing the dirt, then we can say that this is a dynamic equilibrium. Chemists make their living on tricks to prevent equilibrium, to knock it out of whack, to maximize the concentration of the chemicals they want to produce at the expense balance nature seeks. For example, we can consider the Haber process. As nitrogen and hydrogen react to form ammonia, the concentration of those gases begin to decrease, making it less likely to collide and keep reacting. So the rate of the forward reaction slows down. At the same time, the concentration of ammonia rises and more ammonia molecules are available to break up into reactant gases, and the rate of the reaction speeds up. Eventually, those two processes reach a point where they happen at the same time. So far we know that nitrogen and hydrogen keep combining to create ammonia, while ammonia keeps breaking down into nitrogen and hydrogen at the same time. Keep this in mind, that the reaction never stops. It's just eventually we won't see any changes. That's why reactions are written down with double arrows indicating that the process runs both directions. Chemical equilibrium can be disturbed by the concentration of one or more substance or by changes in temperature or pressure. We tend to say shift in the right of it makes more products, or the shift to the left of it makes more reactants. Le Chatelier's principle. If a stress is placed on a system at equilibrium, the system will proceed in a direction that minimizes the stress. This can happen in many ways. For starters, change in the concentration of any substance in a reaction that can cause it to proceed in whatever reaction it restores it to its former balance. Back to the Haber process, if you were to add more nitrogen gas to the mix, the existing hydrogen will have more nitrogen to react with. Therefore, it would begin to form more ammonia, sending the reaction to the right until the reaction balances itself again. Removing the ammonia will have the same effect. There will be less ammonia to break down, so the formation of ammonia will temporarily exceed the formation of nitrogen and hydrogen, and the reaction again will shift to the right until balance is restored. In 1901, Le Chatelier tried to invent a process for fixing nitrogen to make ammonia from nitrogen and hydrogen, but gave up after the experiment caused a huge explosion that killed one of his lab assistants. 8 years later, the German chemist Fritz Haber was able to do what Le Chatelier was trying to do. With his success, Haber's process was used to make chemical explosives which killed hundreds of thousands of people in World War I and II. In addition, the Haber process also saved uncounted millions of people because the ability to fix nitrogen has made chemical fertilizers possible and basically revolutionized modern agriculture. Some impacts he made in society were ammonia is used to purify water supplies as building blocks in the manufacture of many products including plastic, explosives, fabric, pesticides and dyes, and also in household cleaning products. Back to Le Chatelier, despite his great contribution of our understanding of equilibrium, consider his failure to find the efficient method for making ammonia to be the greatest blunder for his scientific career. One of the achievements that Haber made was figuring out a way to continuously remove ammonia as it was being produced, in other words, preventing the process from reaching a state of equilibrium. Changing concentration is actually one-third of the story. Back to the Haber process, for example, you can see that 4 molecules of gas react to form 2 moles of gas. The forward reaction decreases the volume while the reverse reaction increases it. Increasing the pressure will then put more stress on the high volume reactants than the low volume products. So the reaction shifts to the right, producing more ammonia than it does at low pressure. Decreasing the pressure has the opposite effect. The reaction proceeds in the direction that raises the pressure back to where it was before. In this case, the breakdown of ammonia from the left, where the 4 molecules of gas, solid and liquids, aren't affected by the pressure as much. The more gases that are present in the reaction, the greater effect any pressure change will have. Temperature changes. The basic idea to keep in mind is that endothermic reactions which consume heat are favored if heat is added, so higher temperatures tend to feed endothermic reaction. Endothermic reactions which release heat far better than low temperatures. Since endothermic reactions produce heat, the heat tends to favor the reverse endothermic reaction. If heat is added to the reaction, it forces the reaction back to the left. If heat is removed by cooling the mixture, the reaction will proceed to the right. A more interesting reaction involves 2 different ions of cobalt that reach equilibrium in an endothermic reaction. As you can see, one of the ion is pink and the other is blue. If you add hydrochloric acid, it will push the reaction to the blue side. If you add water, it will push the reaction to the pink side. So equilibrium isn't about staying the same all the time. It's just about staying balanced as your circumstances change. Did I miss anything in my presentation? If not, here's another question. Do you believe that our understanding of equilibrium will continue to grow? Thank you for listening to my presentation and I hope you have a wonderful summer. Thank you.